24?
24, yeah.
She said no.
So, first thing I would do is factor to see if there's any reducing that I can do. So I can take out a greatest common factor of x, and then what's left would be a difference of 2 squares. But there's no factors that are identical, so there's no reducing to do, so that's fine. So for my vertical asymptote, I set the denominator equal to 0, and I get -1.
Yeah.
For my x-intercepts, I set the numerator equal to 0 and solve, so I get 0, 0, I get 2, 0, and I get -2, 0. Everybody's good there?
Can we write those just like x equals?
I mean, you can. I just write them this way so I don't get confused about my asymptotes and x-intercepts. But it's fine to write them just x equals. That's okay. My y-intercept is also 0, 0. Shockingly, there can only be one y-intercept in a function. We already have it as an x-intercept also. And then the last thing I need is that other end behavior. We notice here that the degree of the numerator is greater than the degree of the denominator, so we need to do our polynomial division to find that asymptote. Thankfully, this can be done using synthetic division, which is how I would choose to do it. So you'll notice that I had to include some extra zeros there when I did my synthetic division because we have no squared term. It needs a 0 between the x cubed and the x term. And there's no constant term. So I also need a 0 after my x term. Everybody good with that? Okay. Well, let's rip through this synthetic division then. So this is the part that I care about. So there's my asymptote. Everybody okay there? Okay. In order to graph this, I'm going to need to find the vertex. So the vertex is -b over 2a. So -1, or negative of -1 over 2 is just 1/2. I plug 1/2 in and I get -3.25.
Wait, what did you just do? That's not.
So the x-coordinate of the vertex is -b over 2a. So that's going to be negative of -1 over 2 times 1. So 1/2. And then I just plug the 1/2 back in for x to get the y-coordinate. So 1/4 minus 1/2 minus 3 is -1 or 3.25. Okay.
I thought the x would be 0 for b.
Well, the b is this, right? It's the coefficient on the x. I'm graphing the.
No, I mean the b or whatever is below that, the 1/2 and then the order there.
Yeah.
I thought x had to be 0.
No.
Oh, okay. So how did you get 1/2? Sorry.
-b over 2a.
Oh,
That's the formula to find the x-coordinate of the vertex for a quadratic in standard form. the other thing that I'm going to want is the x-intercepts. That should give me a good picture. So to solve that, I will have to use the quadratic formula because that's not factorable. So negative of negative b plus or minus b squared is 1 minus 4 times 1 times negative 3. That's 13 over 2 times 1. So if I go and I type this into my calculator, because I'm going to want a decimal if I'm going to graph this thing. So 1 plus the square root of 13 over 2 is 2.3, and then 1 minus should be negative 1.3. And that should be enough.
What do we just find?
That's what I'm going to use to graph that other asymptote, the quadratic. So those are the x-intercepts for that. And then I have an x-intercept at negative 1. I'm sorry, vertical asymptote at negative 1. And then I have this this parabolic asymptote. So I have 2, 3, 1, or negative 1.30. And then 1/2 and negative 3.25. So there's that. Now I need to draw the rest of my graph. So I had zeros at negative 2, 0, and then positive 2. So here again, I think I can do this without having to draw or having to calculate figure out what's going on at any of the asymptotes because of where the zeros are located. So I know that if I look at the left side of x equals negative 1, it can't be coming from up here to get to the x-intercept because it would have to cross the parabola. So it has to be coming from down there. So it's going to be doing something like that, kind of following the parabola. Is that okay? And then inside here, again, I know it can't be coming from the negative end of negative 1 because it would have to cross the parabola to get to that x-intercept. So it has to be doing something like that. But what I don't know is what's going to be happening out at the end here. But that's okay. I actually do know enough to draw it. Actually, I don't have to do that because this end is going on forever. Oops. That end's going on forever, so that'll cover all the x's out there. Actually, I lied. There's no more piece to it. It's just that. Is that okay?
I have one more question. It's pretty simple. You don't even have to do it. Can you go to number 15 in the odd solution?
Okay.
Is there a hole where that crosses the asymptote, the horizontal one? And why is it able to go through that?
So these asymptote end behaviors
Yeah.
aren't necessarily asymptotes.
Oh, okay.
So like at the ends, it's going to act asymptotically, but in the middle, you might get something like that where it has to cross.
Oh, okay.
And in particular, you know that that was happening right from the get-go because you would have found the horizontal asymptote at y equals 0, and you would have found an x-intercept. Right? You can't have the x-intercept is telling you that it's crossing the asymptote, right? So it's not actually an asymptote, it's just like asymptote light, where like the ends are asymptotic, but the middle maybe isn't. Does that make sense?
If you were to do one of those parabola ones, could I don't know how that is.
Okay. Yeah, technically speaking, like any of these with like the slant ends,
Yeah.
it like conceivably you could have a situation where it crosses, but you won't run into them.
Okay.
The same thing with these things. Like it's possible that you can have a situation where if it can cross, but I wouldn't give you that. You know what I mean? Like these things can get pretty terrible looking. Like that's certainly possible, but I'm not going to give you something that's absurd. You know.
And then, how do you know when you can do this synthetic division again?
So the denominator of your fraction has to be degree 1 with leading coefficient 1.
Okay.
And then you can do synthetic division with no modification. If the leading coefficient isn't 1, you can still do the synthetic division, but it's a little bit trickier. You have to do some modifications. But if the degree isn't 1, there's nothing you can do. You can't do synthetic division with it. You have to do long division.
And then last question.
Yep.
What happens? So I assume that -3 on the synthetic division is the remainder.
Yes.
Do we worry about that at all?
Does not tell us anything
Okay.
as far as the graph goes.
Okay.
Cool. Sophia, did you have a question too?
No, not this question.
Oh, well that was convenient.
You do 21 as well.
Sure.
Another.
Let's see. Y equals x squared over x minus 1. So obviously there's no factoring to do, right? So we'll go straight to the vertical asymptote at x equals 1, setting the denominator equal to 0.
Yeah.
The x-intercept is at 0, 0, where I set the numerator equal to 0 and solve. The y-intercept also is obviously 0, 0, right? And then I just have that asymptote end behavior piece. So again, the degree of the numerator is greater than the degree of the denominator. So I know I have to do the polynomial division here. And I notice that I can do synthetic division, so I'm going to do it that way. So notice I need 2 zeros at the end because I need a 0 for the x spot and a 0 for the 1 spot. Easy to forget to do that. So there's my asymptote end behavior there is y equals x plus 1. So So that's all I need. Let's draw a graph then. Oops. Make that black. So I have an asymptote at 1, or vertical asymptote at 1. And then I have this other asymptote at y equals x plus 1. I'm just going to use the x and y intercepts of that. So that's 0, 1 is the y-intercept, and negative 1, 0 is the x-intercept. And then I have 0, 0 is my x and y-intercept. So I can tell one end of my graph without having to do the limits, because I know that I can't start up here and hit that one because I'd have to cross. So I must have to do something like this. Again, if you did the limit on your calculator, that's fine there too. The other piece, though, I don't know what's going on, at least without checking the limit on my calculator, so let's do that. That stuff. We'll do, what was this, x squared over x minus 1 or something like that, right? So then I need to check what's going on close to 1 on the right side, so maybe 1.1. Getting a negative, or getting a positive value. But let's just check if we get a little bit closer, make sure it gets more positive. So let's do 101. And it did get more positive. So I'm quite convinced that this is what's going on. Okay with that?
Yeah.
And that wasn't so bad, right, in comparison to the last one. Quite a bit less going on. Much easier to graph the asymptotes anyways, right? Graphing that parabola is kind of a hassle.
For the second asymptote, since the equation was y equals x plus 1, how did you get, like, I understand getting like the 1 point, or like,
I picked, for the other, I picked 0 for 1 and then negative 1
like
for 1.
plug in.
Yeah. It's just a line, you just need 2 points.
Yeah.
Usually I use the x and y as intercepts for it because they're easy to get.
Yeah.
And usually if I pick them farther apart, I can draw a better line. In particular, if the slope is something here like 2/3. I try to pick them kind of far apart so that if I'm off a little on my scales, I can still get a good, you know. Cool? Anybody else before we move on to the next stuff?
What's the movie that's good?
You can watch a movie from 2:45 to 7:45 anytime you
That's a
want.
Long movie.
Yeah, probably like Lawrence of Arabia or something.
It's like Justice League and you.
So 2:45 p.m. to 7:45 a.m. Yeah.
Oh, okay.
Basically, the whole time you're not at school is what I was telling him. Because he was asking a silly question, so I didn't listen to the answer.
Yeah.
It was
A little bit
it's
silly
a
to
given.
feel a little
I
bit.
wasn't very, yeah.
The AMs and PMs definitely made that kind of confusing.
Easy part.
Okay. Okay. Today, we're going to talk about solving rational equations. And basically my plan here is to just kind of go through and do a couple of examples to show you kind of how things go. And we can talk about the different techniques that you could possibly do to do some of these examples, but overall I'm just going to kind of burn through this pretty quick, okay? If you have questions about things, so feel free to holler up. Actually, before we do the examples, let's just talk about kind of the methods that you might use. So the first method that I would say that, and the one that I prefer to do, is clearing fractions. And then you can you could make a global least common denominator. And I guess that's really the same thing as anything else. That's probably it. Those are the two different ideas. I guess anything else really becomes one or the other of these. You can kind of do those in different ways, but that's kind of the gist of it. My preference is usually always to clear fractions, unless there's an obvious common denominator already made for us. But let's start with something pretty easy. So you could do x plus 3 over x equal to 4. So to clear fractions, what I'm going to do is to multiply both sides of this equation by the least common denominator of all the fractions in the problem. In this case, that would just be x. Everybody okay with that? So I'm going to multiply both sides by x. So when I do that, I distribute the x through. I get x squared plus 3 equals 4x. When I've done clearing fractions, I'm going to be left with a polynomial equation. To solve a polynomial equation, it needs to be equal to 0, so I'll just subtract the 4x to both sides. And now, since this is a quadratic equation, I can either try to factor this, or I can always use the quadratic formula, but this one factors, so that's what I would do. So the two things that multiply to give us 3 and add to give us -4 is -3 and -1. So my solutions are 3 and 1. And when we're getting these, or we're solving rational equations, we need to make sure we check our solutions because we can get extraneous solutions. But the check is easy. You don't actually have to make sure that both sides are equal. All we really need to check is that these solutions don't give a 0 denominator. So all I'm doing is plugging in for the x here and just making sure that I don't get a 0 in the denominator with my solutions, which doesn't happen here with 3 and 1. right? So that's good. Now if I wanted to do the same problem by making like a global least common denominator, let's show what I would do there. So again, that least common denominator would be x, right? So I'm going to multiply x by x over x. Three over x already has the common denominator, so I don't need to do that, anything with that. And I'm going to multiply 4 by x over x. That's going to give me x squared over x plus 3 over x equals 4x over x. Or I can just think about, since those have a common denominator, I can do that. And since everything is over the same denominator, I can just drop the denominator. And now I'm at the same thing that I had before, right? So it doesn't matter to me kind of which one of these approaches you take. They're basically still doing the same thing, right? I like to do the clearing fractions because I think it takes a little less steps to get it to the answer, but they're doing the same thing and it doesn't matter to me. Everybody okay with that? So let's do another. What would be the least common denominator for all the fractions here? X plus 1, right? Everybody good with that? So I'm just going to do clearing fractions this time. I'm not going to do both of them, since I showed you last time what that looks like. So when I multiply through by x plus 1, I get this. Everybody good there? Okay. So I can just distribute through the x. And I'm left with this. Quadratic equation. Again, I can either try to factor this, it might factor, or I can always use the quadratic formula. This one does factor, though. Multiplies to give us -6 and adds to give us +1 would be +3 and -2. So my solutions are -3 and +2. Again, there's only one denominator that I need to check them in, and if I plug -3 in for x, I get -2. That's not 0, so it's fine. If I plug +2 in for x, I get 3. That's not 0, so that's fine. So this one has two solutions as well. Everybody good with that one? Let's do another. So what's the least common denominator going to be for this situation? Well, it might not be entirely clear until we factor that right-hand side denominator. So that one factors x minus 3 times x minus 1, right?
Yep.
So now it should be pretty clear what the least common denominator is. X minus 3 times x minus 1, right? So I'm going to multiply both sides by that. So when I do that, I'm going to get 2x times x minus 3 plus 1 times x minus 1 equals 2. Is everybody okay with how I got that? If you're not, I can explain some more and draw out some more work, but it should be relatively clear. Again, we've done this last year, so it's not like we're doing this from ground zero, so I'm being maybe a little bit glib with my work. But again, it's not the first time we've done this. So let's go ahead and distribute things through. So 2x squared minus 6x plus x minus 1 is equal to 2. And then we combine like terms and move everything onto one side. So that's 2x squared minus 5x minus 3 equal to 0. And then again, we got something that's quadratic. We can try to factor this, which in this case we'd have to do the long kind of factoring because the leading coefficient isn't 1. Or we can use the quadratic formula. In this situation, I'm going to use the quadratic formula because I think it takes no more time than having to do the long factoring, assuming the long factoring is even going to work, which I'm not guaranteed it will. So I'm just going to use the quadratic formula here. You could factor this, though, and it does factor. I mean, I can look at it and tell, but it's not always super duper obvious that that's going to be the case. And the quadratic formula works just fine. So 25 minus 4 times 2 times 3 is plus 24, so it's 49 over 4. The square root of 49 is just 7. So 5 plus 7 is 12, and 12 divided by 3 is 4. 5 minus 7 is negative 2, divided by 4 is negative 1/2. So I have the solutions 3 and negative 1/2. But if I go back and check, what one's going to be a problem?
That one. 3.
3 doesn't work, right? So toss that one out. Negative 1/2 though is fine. Everybody good with y?
Yeah.
Cool. Still doing okay on these? Let's do a couple more. So again, let's clear the fractions. So just like before, I would start by factoring that quadratic, and then it should be easy to see that the least common denominator would be x minus 3 times x minus 1. Really leave myself enough space there. Let's actually do this. I'm just going to make some more space. like that? One note forever, guys. Alright, so I distribute this through. I get 2.5 times x minus 1 plus 0.5 times x minus 3 equal to x squared. Everybody cool? Now I despise having these decimals here, right? That sucks quite a bit. Because if I'm going to try to factor this later, that makes life really bad, right? So what I'm going to do is I'm just going to multiply it through by 2 because well, it's going to get rid of the decimals. You don't have to do that if you're going to use the quadratic formula anyways. If you've already decided that like that's just what I'm going to do, that's okay. You don't need to do that, what I just did. But it makes life a little bit neater if you're not a decimals person. I'm not a decimals person. I just don't like them. Maybe I'm biased against decimals. Who knows? But I'm left with this quadratic. And then if I notice there's a greatest common factor of 2, so I'll just divide both sides by 2 to get rid of it. And now I'll try to factor. Oh no, it doesn't factor. So what should I do? Quadratic formula. So 3 plus or minus the square root of 9 minus 16 is negative 7. And typically we don't report non-real solutions to rational functions. So we would just write no real solution here at the end as soon as we see that negative under the square root like that. Everybody cool with that? All right. Let's do a story problem. You guys hate these. Okay, you want to fence off a rectangular pasture that must be 500 square feet in area. What is the least amount of fencing that you need? Well, I would start by drawing a picture. So here's my rectangle. So let's call that side X and that side Y. Sound good? I thought so too. There's two equations that I can write immediately here. What two equations or two principal measurements can we have for a rectangle? Area and perimeter. So the area for the rectangle is length times width, And the perimeter is 2 times the length plus 2 times the width. So in our situation, we know that xy has to equal 500. Everybody good with that? Pasture must enclose 500 square feet. So the area has to be that. And the perimeter has to equal 2x plus 2y. So my plan here is going to be, I want to eliminate a variable from my perimeter equation, and then look at the graph of that to find the minimum value for x. Everybody okay with that? Or find the value of x that minimizes that, I should say. So I'm going to solve this equation equal to y by dividing both sides by x, and then substitute that in for y. And if I'd like to, I could simplify that down. It doesn't really matter if we're going to type it into our calculator, though. Everybody good with how I got that in there? I'm going to set a window now. So x is the length of this rectangle. What's the minimum value for a length? 0, right? And the maximum length for x could be 500, right? If this is just like a 500 by 1 fence. That's going to probably be way more than I need, but let's do that. The minimum value for y, again, it's a perimeter, so it's 0. The maximum value for y is, well, I don't know, if the x is 5,000 and the y is 1, I guess that's 102, or 1,002, but I'm just going to put it down as 1,000. So there's my function. So I'm interested in finding that minimum value for y, which is right around here. Everybody good with that? So I'll press second and trace, select the minimum command. Left bounds, I'll move my cursor to the left side of this. That's good. Center there. Right bound. So I'm looking, even though this is kind of all in my way, I'm just looking at the y coordinate. So it decreased that time, decreased that time, decreased that time. Now it got bigger, so I know that I'm on the right side of the minimum. So I'll enter anywhere over there and just guess. So the x would be about 22.4 is what my calculator says. And then if I know that y has to be 500 divided by x, y is about 22.3. So what have we found here? the most efficient ratio of perimeter to area is basically a square. What?
Is that usually a square?
Yes. Sophia.
How do you find x again? But are you going through the whole entire calculator thing for what function?
So I pressed second and then the trace button and selected the minimum command.
Oh.
Because I'm looking for the smallest perimeter value. Okay. So that's the gist of that section. That's not so bad, right? The next section, we're going to talk about solving inequalities. So again, I'm just going to kind of do some examples and show you how to do this. So, when we're solving an inequality, we have to describe the parts, or the values for x, where x squared minus 4 is greater than 0, right? Now, there's typically going to be infinite, yes? Typically, there's going to be infinitely many of those values of x, so we're usually going to describe this with like an interval, so a range of x's. Now, if we think about a graph, the values when x squared minus 4 is less than 0 is basically the part of the graph where it's going to be below the x-axis, right? And if it was x squared minus 4 greater than 0, that'd be the part of the graph that was like above the x-axis. So the only places where the graph can go change from below the x-axis to above the x-axis are at the x-intercepts or at some kind of discontinuity like a vertical asymptote. So what I'm going to do is I'm going to find the x-intercepts and any discontinuities like asymptotes, or vertical asymptotes I should say. And then I will pick some test values in between those points on a number line. Now here, my function is quadratic. Are there any asymptotes on a quadratic? No. You goofus. It's just a parabola, right? So all I'm going to do is just set that equal to 0. So I can solve that, say, by factoring. This one you could also solve directly, just adding 4 to both sides and then square rooting, but you've got to remember that plus or minus. So what I need to do then is I need to take a test value from this interval, and this interval, and all I really care about is whether those test values give me a positive or a negative. So picking a value that's less than -2, that would be like -3. Picking between -2 and +2, maybe I pick 0. And something bigger than +2, maybe I pick +3. Everybody okay with that? And now I'm just going to test. So negative 3 squared minus 4 is greater than 0. 0 squared minus 4 is less than 0. And then 3 squared minus 4 is greater than 0. Notice what I'm checking with is the piece of the inequality that's either greater than 0 or less than 0, right? So the parts of the number line that I want are these parts where we're going to get a positive value. Everybody cool with that? So this piece is negative infinity to negative 2. And then I have to be careful. Do I want a parenthesis or a bracket at negative 2? I want a parenthesis because the original inequality is a greater than, not a greater than or equal to. And then I'll have a union. And then here we'll have 2 to positive infinity. And again, I'll use a parenthesis on the 2 for the same reason I used the parenthesis on the negative 2. Everybody okay with that? So that's not so bad. Let's do another couple of examples just to make sure we got it. Oh, I got 3 more examples on here. That ain't bad. So the next one, we have x cubed minus 4x squared plus 4x is less than or equal to 0. I notice right away that this is a polynomial function, right? Polynomials have no asymptotes, so all I care about is where the polynomial is equal to 0. And I would solve this one by factoring, as I heard somebody mention. So I would start just by taking out the greatest common factor of x. And then I'm left with a quadratic that I can factor easily. The two things that multiply to give me positive 4 and add to give me negative 4 is negative 2 and negative 2. So my x-intercepts are 0 and 2. Everybody cool there? Pedro? Certainly. Everybody good with that? So the test values I need to pick one from each interval. So I would pick negative 1, positive 1, and positive 3. Right, I need a test value on each side of each 0 in this case, or x-intercept. So negative 1 cubed minus 4 times negative 1 squared plus 4 times negative 1 is, that's negative 1. If I do the next one, 1 cubed minus 4 times 1 squared plus 4 times 1 is positive. And if I do 3 cubed minus 4 times 3 plus 4 times 3 squared plus 4 times 3, that's also positive.
Why do we do this stuff?
Well, we have to see what parts of our graph fit here.
So it might not actually fit sometimes?
Yes. So the only piece that worked was this piece. That was the only piece that was less than or equal to 0, right?
It doesn't have to be less than or equal to 0. It could be less than.
Less than 0 is less than or equal to 0.
Less than.
Right? If you pick a number that's less than or equal to 5, that number also has to be less than 5, right?
True.
Yeah.
Unless it's exactly 5 or whatever. But. So this piece is negative infinity to 0. Should that 0 be a bracket or a parenthesis?
Bracket.
Bracket, because it's a or equal to inequality. And there's a little bit more.
Oh, not flashbacks. It's period.
What else do I have to include? Well, this section is positive, so it's nothing from there. And this section is positive, so it's nothing from there. But this value right here gives us 0, right?
So it's, yeah.
So I also need to include the single value of 2. Not an interval, that's why I'm using the squirrely brackets, because it's a set rather than an interval. So it's a single value of 2. So that's why they get the squiggly set brackets as opposed to an interval.
Is that the same as writing 2, 2, though?
No.
No.
It would not. 2, 2 is nonsense.
Well, yeah.
So that, now keep in mind that if this was just less than and not less than or equal to, we wouldn't have this part at the end, right? Everybody's cool with y? So this is, in general, this is not difficult, but there are some things that are can be tricky that you have to make sure you're paying attention about. Let's do this one. So I need the x-intercepts, which is just going to be 4, 0. And I need to worry about the asymptote, which is negative 1. Everybody good with that? Okay. So when I write the x-intercept, I'm going to draw a filled-in dot. But when I write the asymptote, I'm going to draw an open dot, just like if we were drawing things on the number line, because this function doesn't actually have the value negative 1, right? That's not part of the domain. Everybody's good? So I'm going to write that as an open circle to remind myself. So I need to pick, a value from, I need to pick 3 test values. So like negative 1. I'm going to pick 0, that's easy to deal with, and then 5. So that would be negative 6 over negative 1, which is greater than or equal to 0. That is going to be negative 4 over 1, which is less than 0. And then I have, 1 over 6, which is greater than or equal to 0. Everybody's okay there? So, I want these two pieces, right? Because those are the pieces where we're greater than or equal to 0. So this first piece is going to be negative infinity to negative 1. Should the negative 1 get a bracket or a parenthesis? Parenthesis, because the negative 1 is an asymptote. Even though this is a or equal to inequality, the fact that that's a location of an asymptote overrides the inequality. This piece, though, is going to go from 4 to positive infinity. Should the 4 get a parenthesis or a bracket?
Bracket.
Bracket. Since the 4 is a 0, that one should match the inequality. Now you see why I used the open circle and the closed circle to help remind myself whether I was going to use a parenthesis or bracket there. Let's do one more example. Sorry, that's supposed to be absolute value there. I forgot the end of my absolute value bar, so it looked like 1x minus 1. You might be going, why the heck did he write 1 in front of the x? That's because I forgot the other end of my absolute value, so that is absolute value is not 1x minus 11, just to be clear. So let's go ahead and do this. So at negative 4, I have my filled in circle for the x-intercept. And at 1, I'm going to have my open circle for my asymptote. So I'm going to pull negative 5. I'm going to use 0. I'm going to use 2 as my test values. So if I plug negative 5 in, I have the square root of negative 1 over 6, which is definitely not greater than 0 because it's imaginary, right? Is it a square root over the negative? Are you good with that? If I plug 0 in, I have 2 over 1, which is greater than 0. And if I plug 2 in, I have square root of 6 over 1, which is also positive. So the pieces that I want then are this middle piece and this end piece. Everybody okay with that? So this middle piece is negative 4 to 1, excuse me. Should the negative 4 get a parenthesis or a bracket?
Bracket.
Look closely at the symbol in the problem.
Parenthesis.
And the negative, or the 1 absolutely has to have a parenthesis as well, since it's an asymptote. And we'll have a union, and then 1 to positive infinity. Again, the 1 absolutely has to have a parenthesis because it's an asymptote. And that's it, dudes. That was the whole chapter. We just did it all.
That's no product. It's 200.
467 plus 430.
So you guys should be able to do the 25 to 57. now. There are two worksheets that I put in there. I don't think we really need to do those. So we're going to skip the worksheets if you guys are cool with that.
Yeah.
Yes, of course. So don't worry about those. We're just going to worry about the problems. And Friday we're going to do work on stuff day, which feels like a pretty good idea for last hour on a Friday on a week that everybody feels like Wednesday feels like a Friday.
Yep. I agree.
It's just getting worse.
What's getting worse?
School. A lot